Okay, so we're learning a little bit about acid and base reactions. Now we have to be able to determine when an acid and a base react, um, what kind of equation is going to be formed. And in this sense, we have to know how to tell which one's going to act as the acid and which one's going to act as the base. Now, given these two elements here, we have to be able to determine which one will react as the base and which one's going to react as the acid. Now remember, Bronsted-Lowry tells us that an acid donates a proton, okay, and a base accepts a proton. Now we can use this understanding to figure out which one will accept and which one will donate. Now, we also need one other thing. We need our chem data booklet. Now, if you open up your chem data booklet and you go to page 10 and 11, you're going to see all these things listed. Now, understand your strongest acid and your strongest base will react. That just simply makes sense. Now, how to read this table is your acids are listed on this side, just as it says at the top here. These are your acids, and they're all listed here. Now, the topmost left acid is your strongest acid. Now, remember, all of these here are strong acids. If they react with water or a base, they're going to quantitatively 100% react. That's not true when it's a weak acid and a weak base reacting, but that's what happens here. They completely ionize. Now, HClO4 is your strongest acid, okay? And if we scroll all the way down, these are its conjugate bases, okay? Now, the strongest base, as I'm sure we're aware of now, is OH negative. So that means your strongest base is found on the bottom rightmost section. So strongest base. And this can help us identify what kind of equation is going to occur. Because as we look for our bases, we're going to look on the right side. So on this side, okay? And as we go up, the base gets weaker, okay? Which makes sense because strong acids have weak conjugate bases and vice versa. Strong bases have weak conjugate acids. And this guy here would be our weakest base, okay? Now, how do we do and determine what's going to be our weak acid, what's going to be our weak base? First off, we're going to figure out, okay, can both of these possibly be an acid? And if so, which one is the stronger one? So HClO4, this one's pretty obvious. This is topmost left, and this is the strongest acid we can have. So this thing will definitely react as the acid here. So this is most definitely going to be our acid, okay? Now HSO3 negative, we want to make sure that thing can react as a base. So if you go to your booklet, you're going to be looking for HSO3 negative. Okay, so if we're scrolling, HSO3 negative. Okay, so right now it can act as an acid, but it's not the stronger acid, okay? So that means it's definitely going to have to be the base. So we're going to have to look around and try and find where it's acting as a base, because right now this is not acting as a base. This is acting as an acid due to it being on the left-hand side. So HSO3 negative, hopefully I can find it here pretty quickly. Right here. Now it is on the right side. It's not like our redox table. We don't need one over the other in order to be spontaneous reaction, okay? As long as you can find one of the elements on the left-hand side and one of the elements on the right-hand side, then you have a reaction. The one on the left-hand side reacts as the acid, the one on the right-hand side acts as the base. Okay, and of course, this guy here, we might know this word, is an amphiprotic species. It not only can act as a base, it can also act as an acid, as we can tell. But in this reaction, it has to be acting as the base due to the fact HClO4 can only act as an acid since it's such a strong acid. So now we know that this guy is going to be acting as the base. So we can write out our equation as HClO4, and this thing I'm assuming is aqueous, plus HSO3 negative. Now this is a equilibrium reaction, and knowing our Bronsted-Lowry definitions, acids donate their protons. So that means my acid here is going to donate its proton, which is H+, and it's going to form, well, over here, we're going to add on an H. So this will become H2SO3, and recognize that this negative charge is going to get canceled out because it's adding a positive charge, okay? And now we understand that this acid here has lost a H+, so now it's just going to be ClO4 negative, okay? And it's negative because originally it was neutral. It lost a positive charge, therefore now it's a negative charge. Okay, so we can learn a lot about from this question because now we know that this is a base. And if we go back to our data booklets, HClO4 turned into ClO4 negative. Well, guess what? That is its conjugate base formula, if you see that there. So this, of course, is the conjugate base pair to my HClO4. And if we look at what HSO3 negative turned into, it turned into H2SO3. Well, if we look at H2SO3 on the, HSO3 negative acting as a base, its conjugate acid is now H2SO3. And we can see that these reactions can go back and forth, the reversal and the forward reaction. So this guy would be its conjugate acid pair. Okay, so now you've identified the conjugate acid base pairs. You've identified who's the acid, who's the base, who's giving up the protons. If we were talking about the reverse reaction, well, you can see that this guy would be donating its H+ if we were going in the reverse reaction, right? If he lost an H, he would turn into HSO3 negative, as you see here. So again, that's an equilibrium. The reverse reaction is occurring at the same rate as the forward reaction. Now, the last thing I want to mention is which side is favored, okay? So something to understand, the side that has the weakest acid is favored. Weakest acid is favored, okay? Now you might be asking yourself, why is that happening? Why is my weakest acid side being favored? Well, your weakest acid is going to be favored because remember, a strong acid really wants to donate its proton, so it's going to react pretty easily. But a weak acid, wants to hold on to its protons. So that means it's not really going to want to react very much, if any, okay? So barely any reaction. So that means the reaction is going to favor the side of the weakest acid. So we have to take into account all of these. We have to take into account the acids that are occurring, okay? So right now, my HClO4 is acting as an acid, and my H2SO3 is acting as an acid. Clearly, my H2SO3 out of those two acids is the weaker acid. So that means my product side will be favored. And that's because that side has the weak acid, okay? So hopefully that was helpful. We were able to kind of review a lot of different things going on with acid-base reactions. We were able to go over Bronsted-Lowry definitions. We were able to determine using our data booklet what the possible reaction might look like, and we were able to even figure out which side would be favored in this acid-base reaction.